This is a video lecture on solar energy forecasting. And in the previous video, we have talked about general framework, general guidelines, how to develop forecasting models. So in this clip, we will talk about the main techniques that rely on statistical learning methods. These principles can be applied to any type of forecasting model, solar energy or electrical load consumption. So that's why I'm just gonna explain a general guideline that lies within the field of statistical learning. Um, this field, when we take a look at the general mind map, for statistical learning, if you focus on the learning objective, it can be categorized into supervised and unsupervised learning. Supervised learning are the frameworks that requires label or the ground truth of the output variable you want to learn. In the supervised learning, you can split into classification problem and regression. And our solar forecasting technique lie within supervised and regression methods. In statistical learning, there are, if you take a look at the learning methods, they can be split into model-based or and non-parametric. Of course, the first one relies on the parametric approach, rely on the model structure that you would assume, uh, and the problem relies on estimating the model parameter. While on the other hand, for the non-parametric approach, it means that you don't need to make an assumption on a model structure. The learning methods can be split into ensemble and non-ensemble frameworks. For ensemble, it means that you have many submodels that can be trained independently, but somehow at the end you will have a way to aggregate the output of those learners or those submodels. And next, and typically the procedure in the statistical learning uh, can be um, can be detailed in the following process. First, you have to work on the data pre-processing, and you have to come up with a way to develop feature set. Unless right now people may switch into the framework of deep learning that you allow the model that will extract the features for you. All right, but for machine learning algorithm that rely on feature engineering, you still need to do this process. And after that, you train the model, validate the model, and make a prediction. For the data, your data can be time series or cross section. Your data can be numerical data that are mostly typical in engineering, or your data can be categorical. So it's a qualitative variable like genders, like religions, or other things, all right, that are non-quantitative. Um, for um, the procedure in statistical learning start with the data pre-processing. You have missing value, you can decide to neglect them or you want to impute it, remove artifacts. You perform data normalization. You adjust the scale of all the variables to be in the same range. Um, and you prepare the data set for the experiments. That takes a lot of time in my experience. And next, if your model rely on feature engineering, so you have to choose an appropriate set of features. And so it relies on a general guideline as to choose relevant input variable for the output. Or in short, you choose the input variable that highly correlated with the output. But the among the feature set or among the input variable, there should they should be uncorrelated if possible. That means that you only select uh, necessary input variables for the model. So next, you perform the model training. In all of my slide, I will use the variable x as the input, the feature, and we use y as the output or the target or the response variable. And we want to come up with a way to estimate fx that explain relationship between input and output. Um, this is the ground truth relationship f, but that is supposed to be unknown. And what we're going to do is, of course, we have to come up with the structure of f hat, the model structure. For example, you use linear regression model, f hat is simple. You use neural network, f hat is nonlinear, things like that. And if you use a parametric approach, so your your relationship here, f hat, typically parameterized by the model parameter. So what we mean by training a model is basically to choose the model parameter theta so that uh, your y hat is close to the actual y. Okay, so this is a big step. The model training, it requires an assumption on the model structure. It requires optimization technique to train the model. It also requires a good selection of the features. So if you have big data set, this training process takes a long time as well. Okay. Um, once you train a model, and a lot of times you don't train only single model. Maybe you want to try out different things. So you need to perform model validation. You compare the candidate model performance on the unseen data set. There are several methods on the validation technique: leave one out, cross validation, the K4 cross validation, and other things. And once you select the model, the last one is the inference mode. So you're gonna use model for prediction or other purpose. So if you like try to explain like everything in this flow chart. So we start with start with the data set. Mhm. So your data set now you're gonna prepare like in this symbol you're gonna prepare x and y, right? And y is your target and x is your feature. um, so in this diagram it means that this is the raw signal input, and sometimes you have to perform feature engineering. Maybe you for example you can in some applications, you may want to extract features, statistical features like mean variance, other moments, or you want to transform the data into the frequency domain to get Fourier coefficient, or transform the data into the wavelet domain to get the wavelet coefficients. So this is an example of the feature engineering. Whatever feature you think that is correlated with the output. Okay. Um, so we have these data sets, all right, and now you're gonna come up with a way to split them into three buckets. Okay, so this step is important. Typically it requires an assumption that your training data set. What I draw is that the histogram. So if I uh, just draw if I split them, I need to make sure that the data in each set has the same uh, distribution. Okay. In this application, the solar application, I would say that if you have the data set that span, for example, in 1 year, and if you just like use the holdout, so you split maybe the first 8 months for training, the last 4 months for validation and test. So you split it according to the time ordering. Uh, that's fine, but it doesn't guarantee that the data set for training and the test would have the same distribution. Why? Because the weather has a seasonal cycle. So it could be possible that at the end of the year, you have nice weather and maybe the solar radiation has this distribution, all right? While at the beginning of the year, during the rainy season, right? So there were less amount of solar radiation. Maybe the histogram would be like this. Okay, the histogram of solar radiation. So so what I mean is that it makes more sense and it's gonna be a very well controlled experiment if you can just shuffle the data randomly so that, as I say, so that all the three buckets have the same distribution. But this thing also has a limitation as well. Like I would say that preparation of the dataset, sometimes you have limitation on the model architecture. Like the model that you're working on require the datetime vector to be sorted in a time ordering. In that case, you cannot you cannot randomly shuffle the data. Okay, so once you have prepared the data set, now let's talk about the model. Um, I mean, this is in general for any statistical learning technique. When you have prior knowledge about your application, you choose an appropriate class of the model, right? And um, I mean, this step also require um, analysis of your data set. One simple thing could be to try to get the relationship between y and x, like each feature, and see what kind of relationship do they have. If it's nice, if it's simple, you don't need to pick a very complicated model, right? And if if the variable x, if the features are multi-dimensional, maybe you have to pick a more complex model. So once you pick a model type, you pick nonlinear model, you pick neural network, you pick tree, whatever method you pick. So you're gonna perform model training using the training data. But a lot of time, if you use the parametric approach, it means that your model f hat x theta is parameterized by a model parameter. In short, for example, if you use linear regression model, um, if you use linear regression model, um, this is an example of f hat. Your f hat is linear in x, and your beta k is the parameter. Okay, if it's the neural network, if it's a neural network, right? Mhm. So you have hidden layer, you have output layer, you have input layer, and you know that there are weights and bias that are like an amplified gain that of the signal flow from the first layer to the next layer. So in that case, the weight and the bias and of the neural network are the model parameter. So to train a model, a hyperparameter need to be fixed. In short, for example, for linear regression, you have to you have to you have to choose how many regressor you're gonna use, how many variable x. So you have to determine what p you're gonna use. That is hyperparameter. For neural network, you have to pick how many hidden layers how many neurons in each layer. These are hyperparameters that need to be determined. So and of course, and for the a set of hyperparameter also relate to the model complexity. If you pick more hidden layers, your model is more complex. If you choose more regressor in your linear regression, your model is complex. So um, and we and using a more complex model is not necessarily good. There's going to be a trade-off between the model capacity and the model and the model capacity and the model complexity. So it requires a hyperparameter tuning. Mhm. So basically, this one give you a guideline that of how are you gonna pick the complexity of the model. So, but it will be tuned on the unseen data set. So we call it here validation data set. So while you train a model, right? You pick for example, you say 3 hidden layers. Each has 128 neuron, for example. And maybe you have another set of hyperparameter. You vary it to 3 hidden layer, and each has 256 neuron, for example. So you can come up with a systematic way to construct a search space of your hyperparameter. So once for a given hyperparameter, you're gonna train a model based on the training data set, but you're gonna calculate the validate loss on the unseen data set, and you're gonna pick the hyperparameter that the validation loss is smallest. So once you get that, so you pass this box process that is called model selection. Okay. So here you're gonna get a candidate model, and uh, now you perform a model test on another set. We call it test data set. And if the model accepted, you finish the process. If it doesn't, uh, if you don't accept the model, you go back and then you come up with a way. Maybe you modify the class of the model. You pick another method. Okay. So we rely on these flowcharts, and when we talk about technical details of each forecasting method, I will refer back to this flowchart again. Okay. So when we split the data set, there's one common rule. There's one principle that says that um, when you construct a model, you cannot use the test data set or the validation data set in order to construct the model. The model that is trained must rely on the training data only. Okay. That applies to everything. Uh, also include procedures like data scaling. If you perform the data normalization, if you perform the data normalization before training the model. So keep in mind that those normalization factor has to rely on the training data set. Okay. So this statistical learning technique, when we focus or when we talk in the context of forecasting model, and as we have seen before, when we uh, develop a forecasting model, you have to specify the horizon and the resolution of the model. So let me assume that the horizon is H. So a general model description would be it require an input x of t. So I use the notation x of t to notify that you're going to perform of forecasting at time t. Okay, now I'm using this model as in inference mode or the forecasting mode. So that model must release the what we call multi-step forecast output. Um, so it forecasts the y at t plus 1, t plus 2, t plus h. So I use the discrete time index. I maybe sometime I may also use interchangeably between the discrete time index and also sometimes I may use this as well if it's like to to tell exactly what is the time of the forecast value. Sometimes I say t plus 15 minutes, so it's the next 15 minutes. Okay. Um. Okay. So when we have so rely on this at time t, your model is going to give h values. This is y at t plus 1, t plus 2, t plus 3 until t plus h. Mhm. um, a forecasting of is a problem of predicting values of y in the future times. Whatever input that you have here, we also call them regressors. It must follow the principle that regressor should highly correlated with y, okay, with the response variable. This is a typical principle for any statistical learning. The input must be correlated with y. But among the regressor, there should be less correlated. There should be less dependent because it would mean that you don't attempt to add redundant inputs. Um, hmm, for maybe you can think of something like if you want to predict the solar radiation, right? And for example, and if you pick X to be the temperature that you measure at the solar panel. So suppose this is the ambient temperature, right? And you also pick another X that is the temperature that measure uh, at at the nearby building, right? Suppose you pick like X1 and X2. So in this situation, I mean, it. I think these temperature would be in the same range because the ambient temperature doesn't change much in a in a small area. So in this example, X1 and X2 tend to be highly correlated. So you don't need to add two of them. You can pick only one. Okay. Um, okay. Now let me explain about the forecasting principle. So mathematically, let's define input-output mapping explicitly. So we rely on the model description. You're gonna have um, so basically you're gonna have multi-step output. Sorry, multi-step output, right? Yt plus 1, yt plus h. Now we're going to give a detail of the input. So the notation xt that we have here as the input, now it consists a lot of variables. And let me categorize into three groups. The first one, ortho-lag regressors. This means whatever variable that you're going to forecast as y, okay, as y, but is the y in the future times, right? You use the historical data or the lag information that that can be determined by the lag order of ly. So this is called lag order. Sometimes people in deep learning model, people may use the term look back because you want to look back in the history. Uh, And these rely on the assumption that your y, your variable that you want to forecast, has a temporal dynamic. When a variable has a temporal dynamic, it means that the value of yt depends on its own past values. So that's why you attempt to include the past value so that it can help you explain the future. Okay. The second group is called exogenous lag regressor. Exogenous means outside. So this means any variable. Exogenous regressor means any other variable that is not y, um, but you're gonna use the lag values of those regressor variable. For example, in our application, this y is irradiance, solar irradiance. So you may come up with a way to think of what would be another variable that help me explain the irradiance that is correlated with the irradiance. So you can think of what about weather variables? What about the cloud? What about temperature? So these could be examples of exogenous. The third group is called future regressors. So these are the variable, and obviously the variable are not the same as y. These are other variables, but somehow you can measure their values in the future, and you choose the future time to match with the target time in the future. Okay, and again, these variables should be correlated with with your future target. Okay. Let me give an example. If if this application, this is the irradiance, right? You wanna forecast the irradiance in the future, and let's pick an example like t plus one refer to 10 a.m. This is 10:30 and so on, right? And in terms of variable, if we think that the temperature is maybe the clouds. Let's see. If you think that cloud is an important variable that explain the dynamics of irradiance, because more cloud, less irradiance, right? If your target is the irradiance at 10 a.m., what would be the cloud value? What would be the time of the cloud that is highly correlated with the irradiance at 10? Obviously, it shouldn't be cloud at 9 a.m. It shouldn't be cloud at 9 a.m., 6 a.m., right? Because it's too early. It's gonna be like too old, right? If you can, it would be better if you have cloud at 10 a.m., cloud at 10:30, right? Because is the cloud. It should be the cloud dynamic at the moment, at the same moment as you wanna predict these values. However, however, these future regressors, okay, when you develop them, when you select them, you must keep in mind that even though there are values at the future time, you must be able to acquire them at time t, because we perform the forecasting at time t. Obviously, suppose t is 9:30. This is the time we perform the forecast, right? You wanna predict the next step, which is 10 a.m. And you wanna have the information of cloud at 10:30, but you're at 9:30. How can you get this cloud information in the future, right? So it's against the natural, the nature. So that's why these future regressor a lot of times are from synthesized input or from another forecasting models. So I can, in this example, maybe uh, I apply, I buy the weather forecast service. that also release the predicted cloud in the future. So I will use the weather forecast value like from another model. This is not the model that you're going to develop. Okay, so this would be model like I explained before, the NWP model, numerical weather prediction and all that. Okay. Um, there's one note. What else? What else do I miss? The auto lag regressor LY and the exogenous lag order LX do not need to be the same. You can choose it. You can choose them to be any value that you think is appropriate for explaining the dynamics of Y. But sometimes, a lot of time, uh, sometimes you have to choose them to be equal because some of the model technique require them to be so. Okay, but in general, in principle, they do not need to be the same. Mm. I have some guidelines. How to choose the lag order, how to pick the variable. So these guidelines are from the principle versus the the practical guideline. For the lag order or the look back, okay. If 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 naturally your time series Y has long range dependence, it means that YT could depends on the past value, like very past value. So the lag order should be long, right? In principle. Um, But somehow, if you pick the lag order to be long when you deploy the model and you use it in the prediction mode, your platform requires a continuation of the data streaming, which means that either if the missing data occur a lot in the prediction mode, so you have to take care of this issue because because you choose the lag order to be long, right? For example, you wanna so suppose you say that you wanna predict. Suppose I'm here today and I wanna predict 3 days ahead in the red line, and then you say that, oh, my model require the lag order of 3 days. 3 days, okay. So you have to come up with a practical guideline. Like, what if the data discontinue to flow to your system, right? So if this is not obtained, these are not obtained. You still have to. So that's gonna be a problem when you use in the inference mode. I mean, your model cannot release, or you're gonna fake. You're gonna impute the missing data. So it's your option. The variable selection, so the list of the regressor that you're gonna choose in the model. All right. Ideally, you wanna add less correlated input. Sorry. Adding less correlated input. Uh, Hold on. What I mean is that if you pick an input that is is correlated with the output somehow, but the correlation is not strong, all right? It may improve the performance metrics with a small degree. Okay. For example, if you're gonna see in the in our data set examples as well. So if I plot I irradiance and relative humidity, okay. So I might see the scatter plot that looks like this, and maybe the correlation is zero point 0.2 somehow. There's still a correlation, but the correlation is very low. But you also you also choose them, include these variable in the model anyway. When you test the model, maybe the performance metric is improved, but maybe that improvement is not significant. In practice, the cost of acquiring the selected input may be maybe it's not worth it to include in the model. What if that input has to be subscribed from the weather forecast service, right? So you have this when you come up with a way to select model architecture, select the variables, select the feature set, try to think about when to deploy the model as well. And sometimes your feature variables uh, are not free. They have to be purchased from another source, and that has that has a cost as well. Mhm. Um, so I give some example of the common features in solar power engineering. So for the measurements, we have solar irradiance, solar power, temperature, humidity, wind speed, all of the weather variable, the cloud index. The variables that are forecast value, solar irradiant or and the weather variable. So these are from the weather forecast service. They are not measurement value that usually install on your site. The synthesized variable. These are variable that you can compute them, uh, and you can compute them at any time. So these are clear sky irradiance or the trend, the moving average. What I mean is that you can compute the clear sky irradiance of tomorrow or clear sky irradiance next 2 days or even the next year because it comes from a mathematical model. In electrical load, sorry for the typo. For electrical load forecasting, the choice of feature depends highly on the load characteristic. For the residential load, we know that most of the load is from AC, air conditioning. So typically, the main variable is the weather condition or the temperature, solar radiation as well, and the lag consumption, the lagged electrical load power, and the calendar information because you have holidays and it may rely on the assumption that you stay home on the holidays, so you consume a lot, and on work day people go to work, so there's less consumption in your household. On the other hand, if it's industrial load like a factory, okay, so a factory should usually run the machine according to a schedule. So a common feature would be the work schedule, 9 to 5, right? Weather condition and the lag consumption. There are other types of input for the load forecasting as well, and it depends on the horizon. So there are more details on that. For example, if we talk about the long-term load forecasting, like yearly forecast, um, the horizon is in 1 year and the resolution is a month. In that case, economical variable has a very strong impact on the load because we know that energy and economy are the two entities that are closely related. If the economy of our country grows, it means that we have to somehow consume a lot of energy as well. So for the like in a country national level, if you want to predict the load, other common feature would be GDP, CPI, and things like that. All those economic uh, variable. Uh, now, uh, Now, as I mentioned, that for the solar forecasting, this is an example of performing a forecast of one step, just the next time step. The feature from the measurement would be the measurement, the past measurement of I, right? The this is an example. This is the measurement of I at the same time, at the same future time, but it's from the previous day. For example, if t plus 1 refer to 10 a.m., right? This is the irradiance of 10 a.m., but it's from the previous day. Okay. And this is, for example, if your resolution is 30 minutes, your IT is from 9:30, 9, and blah, blah, blah. Okay. You can pick the cloud index or whatever you can extract from the satellite, maybe the cloud images. So that represents one regressor here. And this is temperature, relative humidity, UV, and the wind speed. Okay. Suppose you have sensors. Suppose you have sensor that measure this weather variable. You also have the feature from the forecasted weather. So I use I subscript NWP to refer to numerical weather prediction model. So these are not the same. This is from sensor. This is from the weather forecast. Deterministic feature contains solar zenith angle. Okay, so that depends on the sun position that varies during the day. Okay, so that solar zenith angle gives a trend of the clear sky irradiance. So this is solar irradiance value under the assumption that the sky is clear. So typically, the clear sky model has a very clear kind of a bell curve. Okay, so these are input that come from a synthesized model. People also use a moving average technique, for example, exponential moving average or EMA, to compute the trend. And as I mentioned before, these are future regressors. These are variable that you choose its time to be the same as the target time. But you can compute this value at time t because this from a mathematical model, and the EMA, you have to look at at the detail of the EMA. The EMA only use the past data to calculate, so it can be calculated at time t, but it release the value of time t plus 1. Okay. Once you get the feature set, you may apply this feature selection technique by looking at the correlation, partial correlation, the stepwise regression as well. So these are example in the graph. This is so we plot I irradiance on the y-axis because it's a response, and ambient temp, right? You can see that there's a clear trend. And this is the temperature from NCEP, from NWP model. So you can see that the scatter is all over the places. So it means that it has less correlation. Mhm. This is the solar irradiance from NCEP, from weather forecast model, numerical weather prediction model. So it has a very clear trend. So it has strong correlation. So you may want to keep this as a feature. Relative humidity, again, it doesn't seem to explain very well. Okay, so we may not include it in the model. So that's the scatter plot. This is the time series plot. Okay. So you can see that INSEP has the same trend. Now let me explain the one of the important features for solar engineering, that is the cloud information. Uh, I think the picture is missing here. There's a picture here as well. If you look at the handout that you download from the web, you should see some pictures here. So at our department, we have antenna. We have a receiving station. It receives the satellite signal from Himawari 8/9, and and we have the server that perform the cloud product processing. So mhm, eh, yeah, it's too bad that the picture is missing in my on my iPad. So basically, it's a picture of the cloud, Himawari, and then we perform the cloud index extraction. So so we extract the cloud amount based on the picture of the cloud we see. So we get I mean in our receiving station we can get the cloud mask, and we get the cloud image in RGB format, and we choose the R channel. So once we plot the cloud index, we compute the clear sky index as I divided by I clear sky. So this is K, right? And then we plot the scatter plot between Ci, the cloud amount, and K, the clear sky index. So we see that we have somehow anti-correlation trend. So if there is more cloud, there is less, the sky is less clear. Okay. So you can see from this time series as well. Um, Whenever there is a high amount of cloud, the irradiance is less. Okay. When you read the cloud index from an image, um, I think I would like to show the image. Himawari Optimist dot space. Let me show the Himawari Optimist. Let me go back. Op Optimist dot space. Op op this is gonna be the website that we archive all the satellite images. I'm not sure if it's gonna show or not. Ah, no, it doesn't show. Mm, ah, Never mind. So I hope that you 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 browse this website and you're gonna see some example of the cloud image. Mm. Um, so what I'm trying to say now is that I'm gonna explain the detail of all the features in solar forecasting model. The first one is cloud. The next one is a clear sky model. As I mentioned before, this is called the solar zenith angle. This is the sun position. So the sun position would change during the day. So when it hits 0 degree, which is the sun is on your upright position, the cosine theta, the solar zenith angle, the cosine 0 is 1. It means that your solar zenith angle is at maximum. A clear sky model is a mathematical model that explains the physics of solar irradiance under the clear sky assumption. In the literature, it has many versions proposed by many researchers. And one of which that is very simple to read is from this model. Uh, Initiation, this is from this paper. It says that you have the irradiance constant. So I0 is a constant around one something like 1300 watt per meter square. So this is the solar irradiance you assume at the outside of the atmosphere. Okay. So suppose this is So suppose the sun, oh, like in the earth atmosphere. So suppose we are the earth. In the atmosphere we have a lot of particles, right? So when the sun radiate radiate the ray to our earth, so it's going to go through a lot of particle, right? And those particle will absorb the radiation. Okay, so we have the assumption that the solar irradiance that you measure at the atmosphere would be very high, and that is a constant. And and the clear sky model just basically say that that constant um, will be degraded by this value. This value is exponential function of air mass. These represent air mass, and the higher air mass, that it is less value of this, right? So there is less irradiance when the air mass is high. Also, it depends on this physical parameter TL. This is link turbidity. Turbidity of the atmosphere. Again, the higher value, the less value of exponential term, so it less value in the solar irradiance. There are other parameters, A2, H1, like FH1 and FH2. These constant parameters, they are vary by geographical locations. So in order to use the clear sky model, you need to know the parameter of your air mass. You have to know these two guys and the link turbidity value. So in our group we have applied this model, and we collect the data set under the clear sky assumption, and we try to estimate this link turbidity based on the solar irradiance on our location. So the orange is the clear sky irradiance, and the blue one is the actual one. So you see that for the actual irradiance, sometimes it fluctuates during the day. Maybe at that moment you have cloud like that cover your solar panel. Um, so that's all the features information to that you can use to develop a model. So in the next video, I will explain I will explain the solar forecasting techniques like in overall, and we will give the details of training the model, the machine learning model, in the next video.